Hi everybody. This slide should look familiar. It's where we started the other day. So just a quick little review of what we've been working on. Electromagnets. Just a little reminder that conventional current describes electricity through a circuit as positive charges flowing from positive to negative. But really we know those little positive protons don't move a bunch. It's electrons that do the moving. So electrons are doing the flowing from negative to positive, which is the opposite direction. So again, when you see a little Q with a plus sign and an arrow, we're imagining that that's the way that a positive would go, but really electrons are flowing in the opposite direction. So we watched a little video about Ørsted's discovery, just to talk a little bit more about it. He was putting current through a wire, and when he held his compass a little too close, he noticed when the compass was set below the wire, the needle turned so that from looking overhead, the north-seeking end turned 90 degrees perpendicular to the flow of current through the wire to point with the north moving field toward the left of the positive current flow. So if you look at the picture, you can imagine it that way. If the current is flowing to the left, the north would point to the left of that, like 90 degrees left of the current flow, so kind of towards us. But you notice something also very interesting, which is when he moved it to the other side of the wire, when the compass was brought above the same wire, the north-seeking end turned to the right of the current. So again, the current's still flowing in the same direction, but the north part of the compass is pointing, again, perpendicular, but in the opposite direction. So this is very interesting. You might wonder, why does it happen that way? If we have a field, wouldn't we expect it all to be in the same direction? Why is it changing direction, one above and one below? Well, this led Ørsted to make two very interesting conclusions. Number one, a current creates a magnetic force to which the compass responds. This was surprising and really created an uproar in the scientific community. And then number two, since the magnetic force has opposite directions above and below the wire, vectors of force must form circles about the wire. Now, this is very interesting. Why is this interesting? Because, here, I'm going to grab a little color for us here. If my compass is here, we would imagine it would orient itself in the direction of the magnetic force, right? And again, notice here on top, the arrows are pointing to the left, but here underneath, the arrows are pointing to the right. So you can see we have a bit of a difference here in the direction of the magnetic field, depending on whether we're above or below our wire. So very smart man. Lines of flux are looking a bit different when it comes to a current carrying through a wire. You'll see they make this is exactly the same thing as we did when we sprinkled the iron filings around the magnets, but this time we have a current that's going through a wire. The wire is going straight into the page, as you can see there. A current carrying wire penetrates upward through a surface in a horizontal plane. If we were to scatter those little iron filings all around, you would see these lines of flux make I want you to notice two things about it. Number one, concentric circles. They're making circle inside circle. And notice how the circles get less distinct the further away you are. They start to look like little sprinkles rather than circles. Think about for yourself why that might be. What's happening to the magnetic field the further away you're getting from its source? Might be the same thing as happened with our magnets as well. So very often when we're writing, when we're notating lines of flux, we know how to notate them going in one direction or the other, but what if they were going into the page or out of the page, kind of like we're seeing here? It's coming out of the page or possibly going into the page. The direction of these lines can be found by setting a small compass around the source of the magnetic flux or around the current carrying wire. And you can see if we put a current that's going into the page, we get a positive current into the page, we get what we see there on the left with the little X. It's like a screw, as if you screwed the screw into the page. You can imagine that's the direction the current is flowing. And if you were to put a compass around, it would make a circle around in one direction. And if you reverse the screw as if it was coming out of the page, a positive current coming out of the page, you would notice that the compass actually heads in the opposite direction, right? So when viewed from above, an isolated North Pole moves counterclockwise, and when the current is going into the page, and when the current is directed upwards, and clockwise, when it's, I said that very confusing. Let me try that again. When that's going into the page, you see the north-seeking pole heads clockwise. When it comes out of the page, it reverses direction and goes counterclockwise. And it's because of this kind of screw analogy that the way we notate magnetic fields going into the page is with a little X for like the top of the screw. And the way that we notate it's coming out of the page is with a dot. To imagine that it's like the bottom of the screw pointing at us. So we can see a little example of this here. If the vector is directed out of the page, we see a little dot. And if it's directed into the page, we see a little X for our magnetic fields. And again, that's as opposed to the arrows that we were drawing before. All right, let's watch this little video.
In around 1820, a Dutch physicist named Hans...
Get that going there.
In around 1820, a Dutch physicist named Hans Christian Ørsted made an accidental discovery which opened up a whole new branch of physics that explored the connection between electricity and magnetism. In this video, we'll explore what this discovery was and what were its implications. So as the story goes, Ørsted was doing a demonstration in his lecture in which he had a copper wire through which he would pass some electric current. And on his table, there happened to be a tiny magnetic compass there. Now what he found is when he ran an electric current through that wire to perform some experiment, that magnetic compass deflected. That's it. This was the experiment that led to a great discovery. Now before we talk about what it was, let's go ahead and repeat that experiment. And so to perform this experiment, all we need is a wire, a battery to pass electric current through it, and the magnetic needle. Once we connect this, once we close the circuit, a current will pass through it. And just take a look at what happens to this magnetic needle. All right, here we go. Notice the magnetic needle deflected. That's it. That was the experiment. Now you may be thinking, what's the big deal about this experiment? So what? Well, think about it. So far, we could use electricity to create heat or light. But now for the very first time in the history of mankind, we have discovered that electricity or electric current can make things turn. Can you imagine what could be the applications of that? This principle is used in fans, it's used in your washing machines, in your electric drilling machines, and so on. It's the same principle on which our ammeter and voltmeters work, inside which you pass a current and there's a needle that deflects and shows us the reading. But more importantly, this experiment led us to a huge discovery. What discovery, you ask? Well, let's think about this. What can push on a magnetic compass? Magnetic fields. We've seen before that magnets can create magnetic fields, and when you bring a tiny compass in the vicinity of it, the magnetic field pushes on that compass. But over here, there aren't any magnets nearby. So who is creating a magnetic field that is deflecting this compass? Well, because the electric current was responsible for this deflection, maybe electric current produces a magnetic field around it. And this was a huge discovery. Why was it huge? Well, because earlier we thought that electricity and magnetism were two completely separate phenomena. But now with this single experiment, we are seeing that electric current is producing magnetic field, which means this gives us a clue that there might be some connection between electricity and magnetism. And that's why this opened up a whole new branch of science or branch of physics, which we called electromagnetism, in which we explore this connection between this electricity and magnetism. So Ørsted and probably some other physicists were pretty excited about this discovery. They wanted to learn more about the connection between this electric current and its magnetic field. So they started doing more experiments with this. One thing they immediately realized is that if you increase the strength of the current, then the deflection in the needle also increased. The compass deflected more. This meant that the magnetic field got stronger. So in other words, they found out that if you put more current, you automatically get more magnetic field. It kind of makes sense to me because it's the current that's producing the magnetic field. So I would expect that if the current increases, its effect would be more, and as a result, the field would also increase. Another thing that they found is if they keep the current the same, but they keep this needle at different places, at different distances from the wire, they found that the deflection was maximum close to the wire. And as they moved away from the wire, the deflection became weaker and weaker, smaller and smaller. This meant that the magnetic field is very strong close to the wire, but it weakens as we go farther away from the wire. That's another result. The field weakens with distance from the wire. And again, that kind of makes sense to me. This is very similar to what happens close to a magnet. If you are very close to a magnet, its field is very strong, its force is very strong, and as you go far away from it, the field weakens. And finally, they also want to learn, what does the field look like? What does the magnetic field lines look like? And we've seen before, to draw magnetic field lines, all we have to do is sprinkle some iron filings and see how they arrange, or keep this magnetic compass at different places and look at how it orients. So to do that, they made this wire vertical and made it pass through some kind of a rectangular piece of cardboard on which you can sprinkle iron filings or you can put all your magnetic needles. And when they placed the needles, they found out that the magnetic needles arrange themselves in this fashion. The red represents the north pole of the magnet and the blue is the south pole. Now remember, we define the direction of the magnetic field as a direction in which the north pole points. So over here the magnetic field is this way, this means over here the magnetic field is this way, and so on. And so if we replace these needles with arrow marks that represent the direction of the magnetic field, it would look somewhat like this. Can you see that these arrow marks are running in a circle? And so if we draw a continuous line connecting these arrow marks, we will end up drawing a circle. A circle centered at the wire. And this means that if you want to find the direction of the magnetic field at any point around the wire, you just draw a tangent to this circle. So we draw a tangent to the circle here, you get the magnetic field direction here. You draw a tangent to the circle there, you get the magnetic field direction over there. And of course, we'll get more practice to this, finding the direction of the magnetic field in another video. But this is true at all distances. Even if I were to keep magnetic needles close by, they would run in circles. Even farther away, they would all run in circles. And so the magnetic field everywhere around a straight wire carrying current would be in concentric circles. So that's another result that we find. The field lines are in concentric circles. They all have a center at the wire. And finally, we also saw that the direction of this magnetic field lines depends on the direction of the current. If we were to reverse the direction of the current, the field lines would still be concentric, but they will reverse their directions as well. Like this. And also notice how we have drawn these field lines. The circles are drawn close to each other, near to the wire. This is to indicate that the field is very strong close to the wire. You may remember that one of the properties of the field lines are if the field is stronger, then we draw the field lines closer to each other. And as we go away from the wire, the field weakens, and as a result, we draw the circles farther away from each other. So, what did we learn in this video? We learned that when you pass an electric current through any wire, it produces a magnetic field around it. This connected electricity and magnetism. And with further experiments, we explored the properties of these magnetic fields. And one important property we found is that the magnetic field lines due to a straight wire carrying current is going to be in concentric circles.
All right, I hope that was informative. So now we want to figure out which direction we're going to go with these guys, which direction our current is going to go. We can use what's called Ampere's right-hand rule. So French scientist André Ampère first proposed a method to determine the direction of the magnetic field about a current-carrying wire. He's the first guy to do it. Assuming the current consists of positive charges, again, the conventional way to observe current, Ampere's right-hand rule states that if the thumb of the right hand, everybody take out the thumb of your right hand, is pointed along a conductor in the direction of the positive current, so for example, in this picture is pointing up the wire, the fingers encircle the conductor in the direction of the north moving field. Thus, the north-seeking pole on Ordsa's compass turned to follow the north-seeking field. So again, if we were going to draw our lines, if our thumb is pointing up and we have our fingers curled around the wire, we would see it would be going counterclockwise. Now try this for me. Reverse it. Aim your thumb down. And notice if you reverse the current flow, now your fingers are wrapping clockwise. Because this is a video and I want you to see how this is done properly, let's go, that's audio and I want you to see a video. Let's go watch one more. A demonstration, if you will.
Is the question.
Start from the beginning.
In a previous video, we saw that a straight wire carrying an electric current produces a magnetic field in concentric circles around it. In this video, we're going to see how to remember the direction of the magnetic field due to the current. So let's say this pen represents our straight wire carrying an electric current, and let's say the current is running this way towards the tip of the pen. Then we know the magnetic field around it will be in circles. But that can be in two directions. If I use a bangle to represent the magnetic field, then it can either be this way, where on the top the magnetic field is to the right, as you can see by the arrow mark, or it can be this way, where on the top the magnetic field will be towards the left. So how do we remember what direction it's going to be is the question. So a simple rule that we're going to use over here is called the right hand thumb rule. It says that you take your wire and you clasp it with your right hand, not the left hand, right hand, such that the thumb represents the direction of the electric current. So over here, notice the electric current is this way, so my thumb has to point in that direction. Then the four encircling fingers will tell us the direction of the magnetic field. So over here, notice the encircling fingers are telling me that the magnetic field on the top is to the right. And so now I know that the magnetic field has to be this way, so that on the top it's to the right. And if the electric current were to reverse, let's say downwards, electric current was downwards, now I would clasp the same conductor with my right hand this way, because the thumb should point in the direction of the current, this way. And so now look at the four fingers. The four fingers are telling me that the magnetic field on the top is to the left. Can you see that? It's to the left. And therefore now the magnetic field is going to be this way. Sometimes you have to figure out the direction of the magnetic field at a specific point around a conductor. For example, again, let's say we have a current carrying wire, which is carrying current in this direction. And I ask you, what is the direction of the magnetic field at a specific point over here, to the right of the conductor? How do we calculate that? Well, again, the first step is the same. You use your right-hand clasp rule and figure out the direction of the magnetic field line. It's going to be this way. So it's going to be to the right on the top. And I use my bangle again, like this. And once you have the magnetic field line, to figure out the magnetic field at a specific point, you just draw a tangent to the field line. So I want to find out what is the magnetic field at this point, to the right side. I'm going to hold the conductor this way so I can hold it. All right, so I want to know what is the magnetic field at this point over here. So you have to imagine a tangent to this circle at this point. What would that look like? Well, I'm just going to tilt a little bit so that you can see it properly. If you draw a tangent over here, notice you can draw two tangents, one this way, one this way. But since we already know the magnetic field is going to run like this, the tangent has to be downwards. So the magnetic field to the right of the conductor is going to be downwards like this. Over here, I could have just rotated this bangle also. And notice when I come to this point, hopefully you can see the arrow mark points downwards. So what do you think would be the magnetic field direction at the bottom? Can you try and do this yourself now? Think about this. Pause the video and think about this. At the bottom, over here, at the bottom. Well, again, I'm finding this a little hard to hold. Again, I'm going to hold it this way. Fine. So if you come right at the bottom, again, imagine drawing a tangent over here. What would that tangent look like? Well, I'll tilt it a little bit so you can see. The tangent might be this way or this way. But again, since I know the magnetic field runs like this, the tangent has to be in this direction. Again, I could have just rotated that. And notice, you can actually see the arrow mark at the bottom. It's in this direction. Now, doing it this way, it's fine if you have a prop with you, like if you have a bangle and you have an arrow mark attached to it. But what if you don't have access to it? Imagining this could be very difficult. At least it used to be difficult for me. So I'll tell you what I used to do when I didn't have any props. So again, first step, clasp it with the right hand, same steps. Now, I imagine the magnetic field running like this. So you also try and imagine this. Magnetic field is running this way. Now, instead of a prop, I'm going to use my finger as an arrow mark, and I'm going to run in the direction of the magnetic field, like this. Run in the direction. And now if I want to know the magnetic field at a specific point, I'll just stop over there. So for example, if I want to know what's the magnetic field direction at the right side, I'm just going to stop. And notice, it points downwards. If I want to know what's the magnetic field at the bottom, I'm just going to stop. Hey, it's to the left. If I want to know what's the magnetic field to the left of it, it's upwards, and so on. And so that's how, using the right hand clasp rule and then running your finger along that field line, you can figure out the direction of the magnetic field at any point. So let's solve a couple of numericals now. A wire carries an electric current from west to east. Find the direction of the magnetic field at a point directly below the wire. Okay, so here we have to use east, west, north, south. So just to remember, this is north, this is south, right is east, left is west, up and down. So we have a wire that carries electric current that runs from west to east. So west to east is this way. If this is our wire, from west to east, electric current is in this direction. We need to find the direction of the magnetic field at a point directly below the wire. So we have to find somewhere below it. So pause the video and see if you can try to do it yourself first. Then
Oops, I lost our place, but don't worry, I can find it again. We're pausing the video till we get to see if you can figure out which direction it would point.
direction of the magnetic field at any point. So let's solve a couple of numericals now. A wire carries an electric current from west in a...
Oh, geez, guys, I'm so sorry. I'll try to edit this out later, but we'll try. There we go.
Have a wire that carries electric current that runs from west to east. So west to east is this way. If this is our wire, from west to east, electric current is in this direction. We need to find the direction of the magnetic field at a point directly below the wire. So we have to find somewhere below it. So pause the video and see if you can try to do it yourself first. All right, let's do this. So first step is to use your right hand and clasp this conductor this way. The thumb should point in the direction of the electric current, so it's going to be this way. And so the four fingers are telling me the magnetic field runs in this direction. I'm not going to use any props now. Let's just imagine this. And so the magnetic field runs like this way. And so I'm going to use my fingers to represent that. And since I want to know the magnetic field below the wire, I'm going to stop below the wire now this way. And so below the wire, the magnetic field is to the north. This is not up, this is up, this is to the north. So the answer is to the north. All right, let's solve one more. Suppose you are standing in your room and you find an electron moving from the ceiling to the floor, right in front of you. Find the direction of the magnetic field towards your right. All right, let's think about this. I'm standing in my room over here, and there's an electron that's moving from the ceiling to the floor like this. And I need to find out what direction is the magnetic field to my right side over here. Now you may be wondering, where did an electron come from? Well, remember, an electron is a charged particle, and whenever a charged particle moves, it creates a current. And we know that current produces a magnetic field. And that's how there is a magnetic field, and we need to figure out what direction the magnetic field is on the right side, on my right side. So this is a little bit tricky because electron is a negative charge. So again, pause the video and see if you can figure this out.
Go ahead, pause it.
All right. The tricky part is electrons are negatively charged particles. So if electron is moving downwards, a negative charge is moving downwards, then the direction of the current is upwards. Because you may remember, electric current direction is the direction of positive charge, opposite direction of negative charge. So since electron is moving down, our current would be upwards like this. Okay, that's the only tricky part. And now we have to figure out the direction of the magnetic field over here. All right, so if you have not done it before, now would be a great time to again pause and see if you can figure it out.
Do it, pause.
All right, first step is to use the right hand to clasp this conductor such that the thumb points in the direction of the current. And now the four fingers will tell me what direction the magnetic field is. And so it's telling me the magnetic field runs this way, like this. And so I'm going to use my finger to run it like this. Magnetic field runs this way. Since I want to find the direction on the right side, I'm going to stop on the right, and it's going to be this way. And so that is towards my north. So the magnetic field over here is to the north. So what did we learn in this video? We learned how to use the right hand thumb rule to give us the direction of the magnetic field. Basically, whenever you have a current carrying conductor, you use your right hand, clasp it so that the thumb gives you the direction, thumb represents the direction of the current, and then the four fingers will tell you what direction the magnetic field is.
Come on, that's so fun, isn't it? All right, now time for you to practice. Go to your email and you will find in your email 2 links for Khan Academy little drills. They're super fun. If you get it right, it makes fun sprinkly sounds. Go pause the video now, go to your email and get some practice. Oh, and then come back here because we got some more notes to do. All right. Welcome back. I'm assuming you went and did your practice. I would love to hear how it goes. So maybe write a little note in your margin about deep thoughts, concerns, because I'm very interested. All right. So let's talk about more poleless magnets, right? The lines of flux about a conducting wire, as we learned, are concentric circles, and they do not create identifiable static poles like we would have in a magnet. Instead, the North Pole continually rotates around the wire, right? Thus, the wire, in a sense, is a poleless magnet. The magnetic field produced by a charge moving through the wire is best visualized as a series of rings, as we've seen. So bear in mind that these are just samples, right? It's not like it's only in those locations, right? It's going all the way down the line, these lines of flux, right? And again, weakening as we get further and further away from the wire. Now, what if we made a loop out of this wire? What if we made a loop? All the lines of flux about a single loop of current-carrying wire pass through the loop in the same direction. If you are questioning me, go ahead and aim your thumb up that wire and let it travel around that circle. And notice your fingers keep pointing in one direction through the loop. So the resulting configuration of these lines basically approximate the field lines of a bar magnet. Do you see how that goes? It's coming out the north into the south, making that loop that kind of looks like the magnetic lines that you guys were drawing. One face of the loop basically acts as the North Pole and the other as the South Pole. And if you basically imagine a road running around the outer rim of the loop, anywhere you make a right turn is the direction that would take you north. Now make a few of those loops and we get what's called a solenoid. So basically, if you're taking that same current carrying wire and two loops are formed next to each other, many of the lines of flux generated by one loop link to the other, also achieving an approximate doubling of the lines of flux passing through each loop. The result is a magnet twice as strong as either of the loops individually. A solenoid is a long series, no, it doesn't have to be super long, but a long series of adjacent loops in the form of a helix. Think DNA, the way it wraps, or a loose coil. You can see it here in this picture. When current passes through the wire, the whole solenoid becomes a magnet and a pole appears at each end. North for the whole solenoid is in the same direction as north for even just one of the loops. North can be determined by using the right-hand rule as always. Point your thumb along the current and notice which direction your fingers are wrapping around. I'll give you a second to do that. Give it a shot. Pause the video. Give it a try. Now, from this solenoid magnet, we can make it a lot stronger by inserting highly permeable material like iron into the core. A solenoid with a core of iron, permalloy, or something similar is called an electromagnet. The magnetic field produced by current in the wire magnetizes the iron and gives it basically the same poles as the solenoid. The iron core concentrates the solenoid's lines of flux and further strengthens the electromagnet by contributing many of its own lines of flux to the magnetic field. And whereas a strong bar magnet generates a maximum field strength of about 1 Tesla, an ordinary electromagnet easily generates a maximum field strength of at least 6 Teslas. In fact, electromagnets have been built with the ability to produce temporary field strengths of well over 100 Tesla. Really, extra much bigger. Now, what I would like you to do is pause the video now. And please do the lab. I have put the materials you'll need for the lab and the lab instructions on your desk. Enjoy, and then come back to the video. Bye. Magnetic force. Okay, we know that we have some lines of flux, and the lines of flux are creating a magnetic field. But with that magnetic field, now we will get magnetic force. So early research on the relationship between electricity and magnetism found that magnetic fields appear in the space around every current carrying wire, whether this wire is formed by a straight line, a single loop, or a solenoid. Any two current carrying wires can then be expected to interact like a pair of magnets. So let's see what happens when we have two loops or two solenoids, right? If two loops are energized with a current, we send a current through them, they basically illustrate the same law that we had with magnets, that like poles repel and unlike poles attract. Two solenoids supplied with current obey this law, also just like magnets do. So if you look here, you can see that if we have adjacent loops in a current carrying solenoid that are magnetized in such a way that they attract each other, they'll come together as long as they're not being like held apart by something, right? So if you look here on top, we have a loop in a current carrying solenoids. They're magnetized in such a way to attract or repel each other. Look at the top. We have the currents flowing in the same direction, and they're oriented in such a way that the north-seeking face of one is oriented towards the south-seeking face of the other. They will be attracted. If we have it the other direction, you can see the current is going in kind of like they're going in towards each other, so that the north faces are facing each other, they will be repelled. So here we have what happens when it's not a loop or a solenoid, what happens when it's two parallel conducting wires. So when Ampere of our Ampere's right-hand rule, learned of Oersted's discovery that a compass responds to a current, he immediately performed an experiment to find out whether one current-carrying wire affects another wire. He found that when parallel wires carry current in the same direction, a mutual force of attraction pulls them together, and when they carry currents in opposite direction, a mutual force of repulsion pushes them apart. Try this for me. Take your thumbs, point them up along wire 1 and 2 in figure A. What you'll notice is that when they're heading in the same direction, your fingers, if you wrap them around the wire, mesh together and they point in the same direction. Try this now for figure B, where you point your left thumb up the wire and right thumb down the wire. When you send your fingers to wrap around the wire, you see they clash into each other, fingertip to fingertip, pushing them in opposite directions. So it's possible to talk about what's going on here in math. So please write down this formula in the box. Let's analyze what this is. So the force acting upon a wire segment is found by this. We have our permeability constant for a vacuum, and we have the number there, 1.26 times 10 to the negative 6, and that's going to be our constant of permeability. The permeability of a non-vacuum is slightly less than that number there. If the medium is diamagnetic, slightly repelling, slightly greater if the medium is paramagnetic, slightly attracting, and much greater if the medium is ferromagnetic, super attracting, right? It's basically proportional to the strength of the force. So the other things in our formula we have there, we have I1 and I2. Those are the two currents going through the two wires respectively. We have L, the length of the wire having the force on it, like the length of the wire that we're trying to figure out how much force is on it. And then the denominator, we have 2, which is the number. We have pi, which is the number. And we also have d, the distance between the conductors. So now give a little think on this, right? Consider two parallel conductors carrying the same current, I, whatever that current I is. So our I1 and I2 wouldn't be different. Multiply them together, we get I squared. So you can see that little change I made in the formula right there. It says I squared. If the distance between them is 1 meter, and if they're separated and surrounded by a vacuum, the force upon each meter of length, 1 meter, we can see here. Notice I replaced the length, the L, with 1 meter, and the D also with 1 meter. If I simplify this formula, take a look. we get that the force equals our constant times the current in the wires that are the same, squared, over 2 times pi. We have only 2 variables left. And since the force and the current are the only 2 remaining variables under these conditions, the only 2 variables left, right, being the force and the current, what does that mean for us? Well, this is what amperes start to think about. The relationship between them allows us to define a unit of current in terms of a specific quality of force. It's relating current and force together. So accordingly, we have this SI, a new SI unit, an ampere, and that's the current, the I, that when flowing in each of the 2 long parallel conducting spaced exactly 1 meter apart in a vacuum would give rise to a very specific force, and that's 2 times 10 to the negative 7 upon any meter length of either of the conductors. So although this definition refers to specific values of force and distance, the ampere is not simply a mathematical combination of other units. It's basically elevated to the level of the other 6 fundamental units. So again, to say that more simply, if we're thinking about the force generated in 2 long parallel wires that have the same current, 1 meter apart in a vacuum, the force would be 2 times 10 to the negative 7 Newton on either one of those 1 meter lengths, right? So get used to this. Let's talk a little bit more about the ampere. In a conductor carrying a constant current of 1 ampere, we could say a coulomb is the amount of charge that in each second passes a point on the conductor. Yes? So if you take a look, an ampere is basically coulombs per second. If I rearrange this formula, we can see that coulombs is amperes times seconds. Now this can be confusing since we're defining amperes as coulombs per second, and then coulombs become ampere seconds. It seems like coulombs are moving things, right? But if a coulomb is on the move, it's called current, and we would measure it in amperes. That is why point charges are measured in coulombs. It's a measure of electric charge, whether it is still or moving. So here's a fun little variation on the formula I want you to think about, and we'll pause after this today. But the force on a straight conductor, right? We saw this equation before. Look what happens if I kind of split it into 2 things we can multiply together. The first thing being our constant, our coefficient. We have the current in the first wire divided by 2 pi, the distance between them. This formula alone gives, that part of the formula alone gives us the strength of the magnetic field everywhere along the second conductor. Basically, it's dependent on how far you are from it and how much current is flowing through. The second part, the current in the second wire and the length, determines how susceptible that segment of the wire is to the field's influence. And its susceptibility basically depends on how long it is and how much current is going through it. Again, expressing many of these concepts that we've just been thinking about in math. Okay, we'll pause the video here for today, and I will have written up on the board the questions to answer and the pages they are on. So please give a look up at the board and give it a shot. I look forward to seeing how it goes. Bye.